Okay. I hope everybody enjoyed their 3-day weekend. Did something fun, or at least slept a bunch, got some more rest. This week, we'll be continuing with our understanding of the cardiovascular system, focusing on the vasculature. Ocean somewhere in the back there. Okay. All right. So last week we covered, oh wait. Okay. So last week we were covering relationships between flow, pressure, resistance. And we started to get a handle on some of the blood vessels that we will be relating to these concepts as we try to understand how blood leaves the heart and gets out to all your different types of tissue, how we regulate where that blood flow goes, because blood is really important because blood is carrying the stuff we need, right? Blood is getting oxygen to our tissue. We need that for metabolism. Blood is carrying glucose. We need that. And we're pulling back our waste products. Particularly, we'll focus on carbon dioxide, which will play a little bit of a role today. Okay, so for your warm-up question, this is kind of a prediction, unless you're all caught up on your reading. But because we're focusing on our arterioles at the moment, we had left off segueing into that from our arteries, right? We're going to be thinking a lot about resistance, and we're moving towards regulation of blood pressure at some point. And we took a couple blood pressures in class. Okay, so I want you to recall, right, our big point is that our flow is equivalent to our change in pressure divided by our resistance. Okay? And we know some physiological measurements that we can tack onto this, right? So our blood flow, what we really mean here for our purposes right now, so we're thinking about cardiac output. Okay. For our pressure difference, we're thinking about our mean arterial pressure, so that weighted average, so twice times diastole plus our, what was I saying? Plus our pressure in systole divided by 3. Okay, but we're going to just put mean arterial pressure on top here. And we know that our value for resistance is something called total peripheral resistance, TPR. Okay. So we had begun our conversation with arterioles, thinking about their structure, and in particular, the fact that their smooth muscle in their walls has tone. That tone means that we can get both smaller and larger, bless you, which is going to change the radius of our blood vessels and therefore change resistance. Okay. So we're going to see that resistance is really often the main variable here we're changing. We'll have some changes to the cardiac output and the mean arterial pressure separate from that, but really, really dialing in on this resistance because it's easily controlled by the state of that smooth muscle around arterioles. So we're going to notice that we can reshape this equation, moving that TPR over. So we're going to be able to calculate our mean arterial pressure by multiplying cardiac output times our value for resistance, which is that TPR. Okay. So this is part of why we're focusing on what happens with the muscles, that smooth muscle surrounding the arterioles, because you can see here what we're getting to if we change that total peripheral resistance. Right? When we increase resistance, we may end up increasing our blood pressure and vice versa. So decreases in resistance are going to be correlated with decreases in mean arterial pressure, unless we've got something independently going on with the cardiac output. Okay, so that's kind of where we're going and why we're thinking about the resistance of the arterioles so much. Okay. So our arterioles, we mentioned, are resistant vessels. They're part of the microcirculation, so you don't see them. They're connecting us to our capillaries, which is where we're going to see substances, and particularly fluid, but also gases, also other metabolites crossing the walls of the blood vessels. And we are able to regulate flow to these capillaries largely by changing the contraction of the smooth muscle in the arterioles that goes to them. Okay, so we saw arterioles are really what's giving us most or the majority of our total peripheral resistance. So there is resistance in our other blood vessels, but more than 60% is due to our arterioles. We got a nice drop in pressure across the arterioles, allowing blood to flow through those arterioles. And this is kind of where we left off. Okay. So we were thinking about changes in arterial radius. We mentioned that we have a baseline tone, right? And when we vasoconstrict, we constrict down, we end up increasing resistance, therefore decreasing the flow to organ systems. When we dilate, we see that the sort of sphincter surrounding the arterioles gets wider, so our radius is getting larger, meaning we see increases in blood flow to those arterioles and the capillary beds that they're going. So now we're thinking about the regulation kind of pieces. Okay, so you're gonna want your blood to go to the organs that are working, to the organs that are doing stuff, right? So you're gonna want oxygen and glucose going to your heart if it's beating hard. You're gonna want oxygen and glucose going to your muscles if you're starting to work out, if you're starting to lift. You're gonna want blood to go to your digestive system when it's time to digest stuff. So the way we're able to kind of shunt blood flow to the organ systems that are working more is by varying the resistance of the arterioles that go to the capillaries in those organs. And so when we think about an individual organ, we can think about its flow independently. So in this case, you wouldn't put in, this is our same equation, our flow equation. All right, so this is still just flow is equivalent to a difference in pressure over resistance, right? But now we're thinking about flow to the organ. We're still gonna usually use mean arterial pressure as our delta P. So we have that pressure coming from the arteries versus our very low pressure from the veins on the other side. And we're gonna vary organ resistance rather than total peripheral resistance here on the bottom if we're thinking about organ blood flow. And this is our goal, which also means that we're going to be able to vary the constriction and dilation of groups of arterioles separate from the system as a whole. All right. So an example of why this is important, right? So we're thinking about the systemic circuit for our purposes right now. So we've got arteries coming out of the heart, starting with the aorta, then branching, arterioles, and then capillaries in each of our organs and their capillary beds in parallel to each other. So you don't have to go through organ A, then organ B, then organ C. You're going through each of them at the same time, okay? So this is why we can use that delta P, or our mean arterial pressure, as kind of an estimate across our organ system in general, right? Because we're getting independent flow to each of these, right? So all of these vessels before we start our branches are roughly at our mean arterial pressure, okay? All right, so we're not dropping in pressure as we go down in particular, all right? We're just going across to the veins, coming back to the heart. So this is our system, right? Now, we're gonna see not all your blood vessels are the same size. You've already seen that in lab, right? So we're going to have blood vessels of different sizes, different radii, they're for different diameters, they're for different amounts of resistance to different organ systems. That's fine, that's normal. Okay. We're gonna have a kind of baseline distribution of blood here. So in this example, we've got a little difference in our blood flow between A, B, and C. All right, we have this same difference in pressure, but we have differences in flow because we have differences in how wide these blood vessels are, right? So A is getting the most here because we've got a big old radius, which means we're kind of like more dilated. We have lower resistance, therefore larger flow. So we can see in this example, we're getting 1.5 liters per minute of blood to organ system A. So that's like 50% of our total blood flow in this example. In B, we have slightly smaller blood vessels, slightly more resistance, therefore slightly less flow to B, and then even less to C. Okay. So this is our baseline, and the total flow, 30 liters per minute. So what we're going to think about next is what happens if we change the radius of one of these blood vessels, therefore change the resistance, and therefore change our overall kind of setup here. When we're thinking about organ systems and how we're shunting blood to specific organ systems, this is basically what we're doing. Right? So in this example, we've applied more resistance to tube B, organ system B here, because we've decreased that radius, which means we had an increase in resistance, which means we lowered our flow. Right? So we can see that decrease in flow here. Before we had 1 liter per minute, now we're at 0.5 liters per minute. Okay. So our total flow is just the flow through all of our organ systems in summation, right? We can just add them up. So we can see that the total flow dropped a little bit here, right? Because we lost some flow here because we have more resistance overall in our system, right? So in this case, we weren't keeping our cardiac output consistent. Okay. But more importantly, for our purposes right now, at least equally importantly, is we can see that this has caused a shift of the percentage of blood that's going to our other organ systems, right? So before we were at 50% of blood flow going to A, now we're at 60%, right? So the blood that's remaining is going to A, and we see a little more going to C than there was before as well. Okay. So we've changed the proportions of blood going to each of these organ systems. Now, that would still hold true if we were keeping cardiac output constant, right? We'd have shifted the percentage of blood, increase going to A and C, lowering down B a bit. So this is how we could have more of our blood go to the organ systems that need it, basically. So in this case, we've basically got an example of where we don't need so much blood flow at B. Questions about these relationships so far? Okay. All right. So we're going to think about how our body knows to do this, right? So that's really what we're thinking about when we're thinking about control regulation, starting with our intrinsic control. So when we think intrinsic control, we're thinking local factors. So when I mean local factors, I mean like the signal is coming from that blood vessel itself, pretty much. So right there at that spot, without nervous input, without hormonal input. Okay. So we're going to have some local factors that are going to change the state of that muscle, right? So they're going to change how big that radius is, just depending on that tiny little local area, the relationship between that blood vessel, so our arteriole coming in, the capillary bed next to it, and the tissue lying on top. Okay. So we're going to change the contractile state of smooth muscle with these kind of local signals, therefore changing how much blood flow goes to that local area, right? So anytime we make that radius smaller, right, we're going to get less blood flow. Anytime we make that radius bigger, we're going to increase the blood flow. In general, the reason you would want increases in blood flow to a local area, so whether it's like a patch of your arm or whether it's a whole organ system, is that you have tissue that's doing something, right? So you have an organ that's doing something, you have a region that's doing something. When your cells do stuff, they need energy, they need ATP, which means we need to make ATP, right? So we need to do our whole metabolic process, our whole cellular respiration, possibly aerobic cellular respiration, what we're going to be thinking about here. So our big bang for our buck using the electron transport chain, oxidative phosphorylation, oxygen to produce lots of ATP. We're going to want blood flow, bringing that oxygen, bringing that glucose so that we can continue to have those cells be active and do whatever job they need to do right now. This means that our local signals are going to be signs of increases in metabolism. Okay? So our main signals indicating we need to start dilating our arterioles in an organ system, right? So expanding their radii, dropping their resistance, increasing their flow, are products of metabolism, and particularly we're going to be interested in carbon dioxide. So we should remember, or I'm going to tell you now, so remember after I say it, right? When you break down glucose, right, you get ATP, we know that, but you also give off waste products. So your carbon dioxide is one of those waste products. You got rid of the carbons that were in the glucose and you breathe them out. Okay? So anytime we see increases in carbon dioxide, that's usually going to be a signal that that tissue, that area is making more ATP than it usually is. Increases in potassium ions, hydrogen ions can also be related to increases in metabolic activity. I won't go through the details of that right now, but these are all signals that you have an organ that's doing stuff. So you need more blood flow. So you're going to want to drop down resistance to increase that flow. Now, when tissue kind of resting, not doing much, doesn't need as much ATP, that means it also doesn't need so much oxygen. So in the case where we have less active tissue, less metabolism going on, less ATP production, because we're not doing stuff, this means we may see that we're actually getting extra oxygen to that area, right? Our blood flow is kind of too much. A signal for having kind of too much blood flow to a region would be you're not using all the oxygen that the blood is bringing to you, in which case that blood flow, maybe we need to send that to our brain. Maybe we need to send that to another organ, right? So when we see signs of decreases in metabolic activity, we're going to want to vasoconstrict those arterioles. So we're clamping down on the blood by increasing resistance, moving less flow to that organ system so it can go somewhere else. So that's the big picture that we're looking at as we go through our two examples of intrinsic control over the next several slides. Okay. So we're going to see two types of hyperemia here. Okay, so hyperemia, they're basically going to work the same. What we're doing is we're changing the arterioles so that we can put more. So that's the hyper, that's the increase. Anytime you see emia at the end, this often relates to blood. So like when you're anemic, when you have anemia, that's telling you something about oxygenation and red blood cells in the blood. In this case, hyperemia, active or reactive hyperemia, we're talking about increase in blood flow to a region. Okay. So in active hyperemia, we're going to have increased blood flow because we are active, right? So this is, you are out doing stuff, you're going on a run, whatever it is, you are active. Tissue is active. When I say the tissue is active, I mean it's metabolically active, right? So it's making a bunch of ATP, which means we want more blood flow. So the differences between our active hyperemia and later on our reactive hyperemia are going to be the cause of the increased blood flow rather than really the mechanism for that flow. Okay. So we're going to imagine a steady state system. And you got this in better pictures on your future slides, but I'm going to draw it out first, just real quick. Okay. So we start out with some blood. Here's our blood. It's delivering oxygen and carbon dioxide to some tissue. Or sorry, it's delivering oxygen, I should say. Okay. And it's taking away the carbon dioxide. So we've got this trade here. Okay. So you breathe in the oxygen, you bring it to your tissue. After you deliver the oxygen, you're picking up carbon dioxide so you can breathe it out. So we're going to put some tissue here too. All right. So ideally, at a steady state, at our kind of baseline, you're using up all the oxygen you're bringing, and you're taking away all the carbon dioxide being produced. So we want like a one-to-one exchange between oxygen being brought here by the blood, taken up into tissue, and that oxygen actively being used by the tissue to produce ATP. Okay. Now, the situation we're going to see in active hyperemia, anytime we have an organ system that suddenly needs to make more energy, right? We're increasing our metabolic rate, we're doing our metabolism faster, which means that we're going to start to have a lag of how much oxygen is being used versus how much is being delivered. So we're going to start to have a problem where we need more oxygen and we're kind of using it up. So when we're talking about muscle fiber types in ANP1, right, we saw one way to deal with increases in oxygen demand was to have myoglobin reserves in our oxidative fibers, right? So we have ways of overcoming this, but we have this problem where we don't have enough oxygen. And on the reverse side, we're going to start to see a buildup of our waste products, right? So we're now going to have lots of carbon dioxide, extra carbon dioxide, right? So we're not pulling that carbon dioxide out as fast as we need to be. Okay. So our response to this is going to be, we change the amount of blood flow, right? If we increase the size of that blood vessel, we get more blood. More blood means more oxygen. So we're solving that side. And as more blood flow is passing by that tissue, that means we can carry away extra carbon dioxide too. So we solve both our problems here with vasodilation. So that's the big picture here. So this is how we can react to tissue that's making more ATP. Okay. So here we have in your book how they illustrate this. So in this picture, what we're looking at is we have our oxygen in this blue purple, right, going into our cells. So this is our active tissue, right? That is coming from the blood. Specifically, our site of exchange would be the capillaries, which are going to be right after our arterioles, right? So we can see in this steady state condition, every oxygen molecule that goes in has an equal number of oxygen molecules being pulled in by the tissue here and used. Okay. And on the opposite side, we can see our carbon dioxide. So our carbon dioxide is this green stuff, right? So we can see that we have this one-to-one relationship between carbon dioxide being produced and we gotta go all the way over here. But here we see that carbon dioxide being taken up by the blood, moved away. And we got one more. Okay. So it's not to say that there would be no oxygen, no carbon dioxide in this extracellular fluid ever, but we're going to keep it at this normal steady state condition, trading evenly between the blood and the tissue. Okay. In this situation, we're looking at an increase in the metabolic rate. All right, so you can see that we've changed our number of arrows, right? So now we're producing lots and lots of carbon dioxide. All right, so that's all our arrows coming out, our waste product. But we're still only taking up a little bit of that carbon dioxide and removing it in the blood. We got the same kind of problem going on with our oxygen. So we don't have an even trade anymore. We're pulling lots of oxygen into the tissue, but we're still only delivering a little bit, okay? So this is setting up a problem, right? We're no longer at a steady state. We're seeing changes to the concentration of carbon dioxide and oxygen in this extracellular fluid that lies between our capillaries, the arteriole, and that tissue up top, okay? So we can see that we're seeing a buildup here of extra carbon dioxide sitting around, right? And we're starting to see those oxygen molecules disappearing because we're using them faster than we're bringing them with the blood flow. Okay. So here's where we want to change that blood flow, right? So our reaction here is that we're going to use this as our local signal. So there would be like receptors, the ability to sense this change in concentration of the gases. We're going to have a reaction of the smooth muscle. So this change in the relative concentrations of carbon dioxide and oxygen neighboring that blood vessel, right? Lots of carbon dioxide, lots of extra carbon dioxide, not much oxygen. This is how we have that vasodilation happen. So our reaction here, oops, is going to be extra blood flow. Okay, so we're going to see, we're going to see multiple reactions. Particularly, we're going to see an increase in blood flow because we're going to see vasodilation happening. Okay, so I want you to imagine this scenario now. Okay? So we're thinking about, we're going on a run. Yeah, a bunch of oxidative fibers working in our limb muscles. It's going to be a long run, an endurance run. Okay, so they start out, they use that creatinine phosphate system. They do a little bit of glycolysis. They're using up all their oxygen. Eventually, we want them to do oxidative phosphorylation in the long term. Okay, but in the short term, when we start our run, our oxygen concentration is dropping. Okay, and we're going to think about what's happening at the same time. Okay? So we're going to think about a bunch of different regions. We're thinking about what's going on as we have blood coming towards that tissue, what's happening in our interstitial fluid, in our intracellular fluid, what's happening to the blood vessel itself. Another minute, a couple of seconds. I'll talk it through. Okay, cool. Yeah, so what we're talking about here, our overall goal is to vasodilate. I should hopefully be a little bit of a gimme because I accidentally told you as I pulled up the slide. Okay, but what we're thinking about, all right, we have tissue. It's using up oxygen. Okay. But we're using up lots and lots of oxygen. So if we're thinking about our intracellular fluid, right, ICF is our intracellular fluid, right? We see a drop in oxygen concentration, right? Because we're using all this oxygen up ultimately. We're producing lots and lots of CO2. We're going to have CO2 all over the place, right? Tons of CO2. Oops. Okay. This is because we're making ATP, we're breaking down glucose, so that's building up. So this is first going to be true in the intracellular fluid. Then we're going to kind of come to equilibrium, or just try to come to equilibrium with the extracellular fluid that's neighboring our capillary. And so we see that build up. Okay. And what we're going to try to do to resolve this is to make a big blood vessel, vasodilated, large radius, low resistance, lots of blood flow here. Okay. So that's what we see in this last image, right? So in this last image, this is our reaction to that situation, right? So our reaction to having a huge buildup of carbon dioxide neighboring our capillaries, that we are going to dilate this blood vessel, right? So now it's bigger here. This arteriole got bigger. So if we got bigger, we're going to think about the same difference in pressure, right? We get a larger radius. That means we see a drop in resistance. Okay. So when we're dividing the same number by a smaller number, this means we have a larger flow to that organ, right? Because we've got this inverse relationship here. Okay. So now we are pulling that extra carbon dioxide into the blood because we have this increased flow. And we're kind of rectifying this issue of not having enough oxygen. All right. So we used up oxygen, but now we're delivering extra oxygen, lots and lots of arrows coming out of here. Okay. Questions about this system here? So this is basically a property of how the smooth muscle in the arterioles reacts, right? It just is a property of that muscle, of that vessel, that it responds to increases in carbon dioxide by dilating. And that when we have those increases in carbon dioxide, we're pretty much always going to have kind of oxygen deprivation going on at the same time. Okay. So in your book, overall, make sure that you're able to understand and walk through this figure, right? Showing us how we understand active hyperemia. Okay. We just walk through this panel by panel. Reactive hyperemia actually works the same way, right? So reactive hyperemia is a reaction to something. Now we're not thinking about the cause being extra metabolism, extra tissue activity. We're thinking about the reason for our need for more blood. It's a reaction to some kind of reduction in blood flow, to some kind of often a blockage of blood going to that tissue. Okay. So it's a reaction to like an injury or something that has been done to the blood vessels. But from a signaling perspective, blood flow perspective, resistance, radius perspective, it's going to work exactly the same as active hyperemia did. All right, so now what we're thinking about, we're going to have our arterial, right, normal arterial. We're going to have our normal tissue. I'm not going to separately draw the capillaries, but they're there, okay? Cool. So we're thinking about a situation where we had blood flow, we had oxygen coming to our tissue, we had carbon dioxide being removed, but something happened. Say you clamped this blood vessel for a surgery or something. Draw the worst clamps in the world here. Okay. Some kind of blockage. You can just draw an X, right? So in this situation, right, anything past that blockage, right, it's going to rapidly use up the oxygen that's in the blood that's sitting there, right? And it's going to start building up carbon dioxide, right? Because it's still doing something, even if it's just working at its steady state of required ATP production. But since the blood isn't moving, since it's blocked, right, that carbon dioxide is just going to kind of sit there. We're not bringing any new, fresh oxygen to the tissue that's past this blockage, okay? So reactive hyperemia kicks in when we remove the blockage, right? So when we remove this blockage and we basically heal the problem, fix the problem, allow blood flow to return, we're going to try to rapidly make up for this. So we're going to try to rapidly make up for that deprivation by vasodilating our blood vessel, right? So this is still a reaction to an increase in carbon dioxide concentrations, decrease in oxygen concentrations, increasing blood flow by increasing that radius and therefore dropping resistance. The only difference here is that the reason we had that carbon dioxide buildup was different. Yeah. Okay, so the question was whether this happens like automatically on its own or whether we need to do something to be able to make this happen. The answer is this is just how the smooth muscle and the arterioles work. So this is basically kind of a form of homeostasis, right? So this is a way that your blood should be reacting automatically. Good question. When we think about things we might do, interventions we do, that would be more from the extrinsic regulation perspective. This is just a really local response. Okay. So you can see in flowchart form as well, this is exactly the same information as we've seen in pictures and in bullet points, but if we like flowcharts, which we sometimes do, they're nice to kind of blank out as you have them in your slides so that you can predict and make sure that you can walk through this whole kind of information flow. All right, for active hyperemia, we're thinking about increasing metabolic rate, right? So increasing activity, increasing ATP production, which means we're increasing how much O2 we use, so O2 consumption, increasing how much CO2 we produce. All right, so now we have extra CO2 hanging around. So we can see that neighboring that tissue, so first in the intracellular fluid building up, then spilling over as we come to equilibrium with extracellular fluid, or start to try to, because gases can just move across cell membranes. They're nonpolar, they're small. We don't need any transport going on here. So we see our drop in the concentration of oxygen, right? So we see that little down arrow here. Then that arrow, we see that neighboring concentration of oxygen deprivation happening and that buildup of CO2. Okay. So our local reaction, just a property of how the smooth muscle in the arterioles works, is that when they sense this, they dilate. All right, so when they dilate, we're thinking about an increase in little r radius, which we know is inversely proportional to resistance. All right, so when we see radius go up, we see resistance go down. All right, so resistance is going down. And we again have an inverse relationship when we think about resistance going down. That's going to have an inverse relationship to our flow. So resistance going down, blood flow goes up. Okay. So the overall effect here is that now we're making up for that drop in oxygen. Right? So now we're increasing delivery of oxygen. We see that we had a high carbon dioxide concentration. So we're going to increase how fast we're removing that carbon dioxide, putting us back to our original states ideally. So back to higher oxygen concentration compared to that drop, lowering down that buildup of carbon dioxide. So this is overall a negative feedback loop. When we get back to normal, when we get back to steady state, our blood vessel or arteriole is going to go back to its like normal kind of tone, right? So we're going to adjust the size of that blood vessel to how much oxygen is needed, how much carbon dioxide is being produced. So this entire picture is the same for reactive hyperemia. All right, so overall, this whole middle part is identical all the way to the bottom. Exact same thing is happening from the perspective of our arterioles and our gases. We're seeing a buildup of carbon dioxide. We're seeing a drop in oxygen. Okay. The only difference is that the reason for this isn't metabolically active tissue. It's that you didn't have enough blood flow for some other reason. So often we're going to be thinking about blockages, but it could also be like hemorrhaging, blood loss. That's a trickier picture. I'm not using that as my example because before we increase blood flow, if you're bleeding, hemorrhaging, you're going to want to fix the walls of that blood vessel so it just doesn't spill more and more and more. But any decrease in blood flow, when we have a situation where we're able to return blood to that system, we're going to see that rapid dilation to kind of make up for it. Okay. Any other questions here about our hyperemia, active or reactive? Okay, none. Move a little bit further. Okay. So one way we can intrinsically control the distribution of blood to organ systems and control that flow is through these gas concentrations naturally changing as we use oxygen and we produce carbon dioxide as a byproduct of metabolism. Another thing that's true about how the smooth muscle in arterioles react is that we do have some autoregulation of blood flow from the muscle itself. So the myogenic response is going to be a response of that smooth muscle. This is going to be something that happens when we feel stretch. So when that muscle in the walls of the arterioles gets stretched out, it's going to have a response. That's our myogenic response. Okay. So what we're imagining here is we are thinking about a situation where we have increased perfusion pressure, creating increases in blood flow and pressure in arterioles. When we talk about perfusion pressure, I'm going to go ahead and define that first. Right? So perfusion pressure is really just that delta P that we've been talking about, that difference in pressure. We can think about that across the system as a whole, right? So our mean arterial pressure minus our central venous pressure would be a perfusion pressure for like the system as a whole. Or you can think about it for a specific organ, right? You might think about the perfusion pressure across the lungs. When we link this up to respiration and changes in breathing, we will think about that as well. So perfusion pressure is just that difference in pressure we're thinking about. Okay. So in this case, we're thinking about an increase in perfusion pressure. So we're saying delta P going up, right? We know we have resistance on the bottom, right? But when we see that perfusion pressure go up, we see increases in flow. You have increases in how much blood is flowing through an area, right? We know that we have that low compliance in arteries. Our arterioles are a step down from that, right? But we know that that blood in the vessel itself puts pressure on the walls, right? So we're putting pressure on the walls of the arterioles, kind of trying pushing them out, expanding them a little bit as we have this increase in flow. So like we're turning on a fire hose going through the arteries and then into the arterioles. All right, so we've got this stretch to the walls of the arteriole. All right, so here's my arteriole. We're thinking about that increase in flow, pushing out on the walls of the vessel, kind of in all directions. Okay, so it can stretch, right? So we can stretch it out a little bit, reacting to this increase in flow because of this increase in our pressure gradient. Okay. What happens after that though, right? We get stretched out, we got kind of a reflex going on. So the myogenic response is kind of a reflex, clamping back down a little bit, trying to go back to our normal level of contraction, right? So we're trying to keep that blood flow to the organ consistent in this case, in this myogenic autoregulation, right? So we're going to try to keep that blood flow constant at our baseline, at our required level. So that's how we're kind of having a reflex. When we see an increase in flow, think about an increase like coming from the heart, right? Suddenly your heartbeat is going up. In all the arterioles, in the immediate response, we're going to see, oh, we got extra blood. We expand a little, right? Because it's physically pushing on the walls. Not a lot, but a little, right? And that muscle, when it gets stretched, it's going to bounce back. So we're going to vasoconstrict, bounce back, try and put that blood flow back down. So myogenic autoregulation, just muscle created, right? So myo for muscle, genic, think like genesis, generate, autoregulation, so self-regulation. Right? So self-regulation of the arteriole coming from that muscle fiber. So here's how we can think of that here. So we're thinking about increases in perfusion pressure. So increases in that difference in pressure that we're looking at that is ultimately going to increase flow in the short term, right? As we increase that flow, that blood physically takes up space. Extra space means we're going to stretch that smooth muscle, okay? So the myogenic response, right? The myogenic response, that autoregulation. Okay, we stretched out a little bit. Our response here is that we constrict, right? So when we constrict, that means we're reducing the radius, which means we're increasing resistance, right? Which means we are also bringing that flow back down, right? So we had an extra burst of blood. If we don't need that extra blood, we're going to want to put that blood flow back to normal, right? So we react essentially, right? What we had set up here was an increase in pressure, right? So we're responding to this with an increase in resistance so we can keep flow the same. So I'm going to erase this arrow because if we increase them both equivalently, flow would just stay at the steady state. Right? Which unless we have other information from our organ system, that's what we want it to do. So the result of being able to regulate blood flow to different organs by being able to regulate the resistance of arterioles through regulating the radius of that smooth muscle is that we can shift where blood goes kind of all the time, right? But especially we can shift where blood goes as we increase blood flow in a system, as we start to exercise, as we start to change cardiac output, we can also control where that extra blood goes. So we can see here with our normal cardiac output, right, at rest, your cardiac output is about 5 liters per minute, right? So we're thinking cardiac output is going to be our mean arterial pressure divided by our total peripheral resistance. Just a reminder here, okay? So we can see the distribution under our resting state. Here we can see that when our cardiac output goes up, we're going to have a bunch of changes that shift where that blood flow goes, right? So we can increase cardiac output, reminder, our cardiac output is how much blood we're getting moving through our systemic circuit per minute. All right, so this is our blood per minute, measured in liters per minute. All right, so we get that cardiac output by multiplying our stroke volume, blood per each heartbeat, times our heart rate. Okay. So we're going to see that as we see changes to cardiac output, which we know can be varied by changing the stroke volume or changing the heart rate or both, right? We're going to also see shifts in the vasculature that put most of that extra blood to the skeletal muscle. So we're going to finish off with really where we began in that warm-up. So next time we'll be talking about extrinsic control of arteriolar radius and how that relates to our mean arterial pressure. So we're going to remember for next time that we have this relationship between flow. We've talked about it. We have a relationship between cardiac output and our mean arterial pressure and our TPR, our total peripheral resistance. Talked about how that's the exact same equation. And at the beginning, we saw how we can reshape that mean arterial pressure, cardiac output, and TPR relationship so that we can see how changes in cardiac output or resistance would influence our blood pressure. Okay, so we'll start here on Friday. See you guys then.